This is kind of a bonus video that goes over some techniques for designing systems with gain and offset. What I'm going to do in this video is I'm going to go through my example of the project that we're working on. And as I'm doing it, I'm going to use a document that's provided on the Canvas site for designing op-amp circuits to provide a specific gain and offset. So right now, this is I just want to briefly show you this. So this is an application report by Texas Instruments that it's posted on the Canvas site, but you can also just search for SLOA 097. And there's a lot of companies put these out. These are basically short papers that help people who would potentially buy the products sold by companies like Texas Instruments. It sort of shows how best to use their products. And this one is kind of a generic one. This is sort of a broad, it's not really specific to their devices. A lot of these you'll find are, though. A lot of these sorts of white paper application reports, design summaries, reference documents. Quite often these will be things like, if you're trying to do this specific application, like let's say you're trying to build a strain gauge amplifier, some of them will be very specific. It will say, here's how to use our exact product. And a lot of times they'll be kind of a sales pitch. So you have to be a little wary when using these of how much the information is unbiased and how much of it is sort of trying to push you towards a product family or for your design. This one's fairly straightforward though, and I really like this. This is basically just a reference manual for when you're in a situation where you need to take a signal and amplify it, provide gain and provide offset. This is sort of a quick little rundown of how to do it. It's a nice resource in that way. We'll use a couple of these in this class. So we'll use this one. We'll also use for the buck and boost regulators, we'll use a design guide. I think it's also put out by Texas Instruments, but these can be very handy. These are actually typically what engineers will use when they're going to design a product. Is they'll usually, if they don't have a textbook handy that had information, or even if they do, sometimes they'll look for the newest application report or application guide by these companies to sort of see if there's any recommended design ideas. And sometimes these will be sort of practical things. Sometimes these will be, hey, if you build this way, you're going to run into this issue. So maybe add a capacitor here, or if you do this, it might be unstable. So maybe modify this and it'll help improve things. But just to quickly give you a taste for this, this sort of looks at gain and offset as sort of slope and if you go back to when you took probably algebra, right, or and you learned about the slope of a function and the y-intercept, right? Usually those were m and b, or So this document is basically saying how to design a gain, which is the M term, and an offset, which is the B term here. And it's and they split it up into basically if you need positive gain and positive offset, if you need positive gain and negative offset, negative gain, positive offset, negative gain, negative offset. And as something to note is these are just some of the options. There's lots of options for doing this. Another thing to note is when we have op amps, we have the ability to invert fairly easily. And a lot of these designs are not ideal in the sense that some of these designs they talk about in this document have finite input impedance, which means that you probably want to buffer a signal before you sent it to these circuits if it wasn't a strong signal. Some of them require the ability for the input to be able to handle a current flowing back into its terminal. That's not always an easy thing to do. So there also, you'd probably want to buffer a signal. So if we're dealing with a situation where we have to buffer a signal anyway, then, for instance, if we need positive gain and positive offset, doing a negative gain and negative offset, but inverting the signal beforehand, potentially is an option, right? Or doing a negative gain and positive offset, and again, inverting that signal beforehand. So just keep that in mind. We can always use multiple stages of op amps. This design guide is basically for a single stage, how to do these 4 different cases with a single stage op amp with non-ideal input impedance. Okay, so I'm going to take a step back and I want to talk a little bit about the project. So I want to talk about this goal of, let me switch shares here. So I'm going to talk a little bit about this goal of, and I'm going to try not to flip my laptop into tablet mode. I'll try to just do it normally. Or basically we have a signal, and experimentally I found the signal was about between 0.5 to 3 volts. So 0.5 to 3 volts. And we're trying to take this signal, and for me, I kind of found that between 0.5 and 1 volt, that was really sort of the good air quality range. And over 1 volt is really when it was when there was a lot of particulates in the air, when the air was fairly poorly filtered. I did some experiments with these sensors, and actually having non-clean air lingers. I mean, they're pretty good at detecting it. Once you have something that disturbs the air in our labs is fairly clean. They have right now, especially they have the air handling going sort of full blast. So it keeps the air in the room fairly clean. You probably noticed that if you were in the 331 lab. But, any little bit of smoke or any little, if you have a soldering iron and you sort of, touch it to some solder flux and it sort of kicks that smoke into the air, this sensor will detect it. It'll detect it and it'll linger in the air. Basically, as long as you can sort of, smell smoke or something, then it will be a detectable signal from that. But for my design, I wanted to have basically the green LED illuminate between 0.5 and 1 volt, and the red LED illuminate from 1 volt to 3 volts. So that's the way I'm going to do this design. A lot of you did what I said originally, which was like 0.7 to 3.5, and you did 2.2 as the cutoff. That's fine too. So that will work too. That's just going to be the transition from green to red. Is you're going to have some, pretty not super clean air that's still showing up as a faint green. So I'm just kind of in my design trying to avoid that. So the other thing we found is we went over in the lab document is this idea of using a pseudo ground as a convenient way to clean up a signal, or sorry, a convenient way to sort of find we can pretend a signal is a differential signal, which is sometimes convenient if we're using a pseudo ground to do that. So, okay, so this challenge of my signal is 0.5 to 3. One of the biggest challenges you'll notice is we have to keep that signal away from the rails. 0.5 volt signal doesn't give us a lot of headroom away from that 0 volt rail. So sometimes the first thing I like to do is take my signal and shift it across the rails, shift it within range of the rail. So in this case, I want 1 volt to be my sort of inflection point here. Maybe I should have done tablet mode because my handwriting is atrocious here. So I want 1 volt to be my threshold. So I think I'm going to shift this signal up so that 1 volt is basically midway between my rails. So I'm going to shift this up so that 1 volt threshold hits about 2.5 volts. So how could I do that? So basically, I want to take a signal that goes 0.5 to 3, and I want to shift this so that 1 is actually 2.5. So I need to add 1.5 volts to this thing, right? Yes. So I need to add 1.5 volts to this. So my offset's got to be 1.5 volts. And what about my gain? My gain is probably okay as being a gain of 1. So if with a gain of 1, the signal will be between 2 volts and 4.5 volts, it looks like. So that's okay. We actually might, in this case, this might be a case if we were worried about our design getting too close to a rail, this might be a case where we have a gain of less than 1. We might actually want to sort of trim that signal range down a little bit to stay away from those rails. Again, though, the design that we use for our finished PCBs, they'll use rail-to-rail op amps, so we don't have to worry that much about it. But even with rail-to-rail op amps, you generally don't want to operate right at the rail. They're usually weak operating right at the rail. But for now, let's just leave it as a gain of 1. So we have this task then. We want a gain of 1, and we want an offset of 1.5 volts. Okay, let's go back and let's look at that document that we had then. Oops, you're not supposed to see that. That was the circuit design that I did for the project. That's coming up later. There's a video after this that will have that in there. But let me, let's go back to that TI document. Okay, so gain of 1, offset of 1.5, those are both positive. So if we're looking at this document, that would be positive M and positive B. That's going to be page 2. Just not too hard to get to, I guess. So here we are at page 2. Positive M and positive B. So let's look at the circuit they're using for that. This is kind of an interesting circuit here. So this circuit is, so it's just taking a, now this is not an offset necessarily. This is just a reference. We're just taking a voltage, and very likely, usually when you're using a reference like this, you're just going to pick a rail as long as your rail is clean. If your rail voltage is kind of an ugly signal, if it's really jittery and really messy, then you might go with something. You might get this reference signal from like a diode. So a lot of times you'll use like a Zener diode for this to get to use the breakdown voltage across the Zener as a reference voltage. Sometimes you'll amplify the breakdown across Zener for that, and that's basically what voltage references do. So sometimes you'd use an actual voltage reference for this, but we're going to assume for this application that our rails are fairly clean. Even if they're not, this is a sort of this is a system that needs to respond at sort of the speed of the human eye. So even if our power supply has like 100 kilohertz noise on it, we're probably not going to see that show up. I mean, our eyes probably aren't going to be perceptible to that sort of flicker that fast. So I'm just going to use the rail as a reference. So for the purposes of doing this design, this reference voltage that we use to provide the offset, I'm just going to use the 5-volt rail. So then we have R1, R2, RF, and RG. And so it takes us through a step. So it says positive M, positive B. Step 1, choose R1. Just pick one, right? Now, usually when I'm doing these designs, when you get to pick a resistor value, there's a couple things to think about. Usually you don't want to pick one that's too small. If you're picking like 100 ohms, ultimately what that's going to mean is that your op amp is burning a lot of power. It's going to operate with a lot of currents. On the flip side, you generally don't want to pick things like a mega ohm. If you pick like a mega ohm, now your amplifier is going to work with very tiny currents. It's going to be very susceptible to noise. It very likely could be unstable if it's that high of a resistance. So usually something in the middle, 50 kilo ohms, if you have a decent op amp, 50 kilo ohms would typically be like a standard value you'd use if you're just picking one. I'm a little less confident about these op amps, so I might just pick 10K. I might just pick 10 kilo ohms for this. So I'm going to go back to the other slide, and I'm going to start building this circuit. So VN, VREF, R1, R2. So VN. Let me, oops, man, I don't know what's causing that. And then we'll go back to, so that fed into the positive terminal. So keep in mind, this op amp is flipped, RF and RG. So. Okay. All right. So I'm going to be switching back and forth a lot. So choose R1. R1, I'm just going to pick 10 kilo ohms. So I'm going to pick 10 kilo ohms. And again. And then go to step 2. Step 2 is choose or calculate R2. R2 is equal to VREF times R1 times M divided by B. Okay, well, let's do it. So what was our VREF? Well, I said for our reference voltage, we'll just use the rail. So let's just use 5 volts. So we have 5 volts as our VREF times R1, which we'd pick to be 10K. Times M, what's the gain of our system. The gain of our system was just going to be 1 divided by B. So what was our offset? Our offset was 1.5 volts. So I get 33.3 repeating K. So R2, I get 33.3 K. And then, okay, then we go back. So going back, it says select RF, maybe suggested by datasheet. So, and what they're saying is your op amp that you pick might say, if you're using a feedback resistance, you know, use 100 kilo ohms, or, you know, if you get to pick, use something, you know, and sometimes it'll say, don't use a feedback of less than this or greater than this. Not always. Most op amps don't say that explicitly, but usually when you're designing, you kind of know, you know, 20 to 100 kilo ohms, 20 to 200 kilo ohms is sometimes safe. As you get closer to 200 kilo ohms, you got to make sure it's a good op amp. As you get closer to like 1 kilo ohm, you have to make sure the op amp can provide enough current for something like that, and just know that you're going to be kind of burning a little bit of power. Let's just use 10K again. 10K is pretty much always going to be a safe value. It might not be the most power efficient, but it's pretty much always going to be safe. So let's say RF is equal to 10. And then let's just immediately, so I don't have to flip back again, let's just calculate this. So it says calculate RG using this formula. So what was our R2? Our R2 we'd found was 33.3K times RF. RF was 10K. So we remember, we just picked that just now. Divided by, okay, so M was 1, right? So 1 times R1 plus R2. R1 plus R2 is going to be 33K plus 10K. So 43. .3 repeating. Minus R2. And R2 we had found to be, oh, well, that was easy, right? So R1 was 10K, R2 was 33.333K. Times 1 minus R2. So that's just going to be, so the denominator of that equation is just going to be R1, which is 10K. So we find that our RG should be 33.3K. So going back, here, our RF was 10K and RG was 33.3K. Now let's sanity check this. We just followed a cookbook, and I don't usually trust that. I don't like this idea of just taking Texas Instruments' word for it. So we could fully derive this expression, but let's do a test case. So the main thing is, let's make sure that our gain is actually 1. Well, let's make sure that our gain is 1, and then let's make sure that our offset is 1.5. Those are 2 easy checks to do. So let's say, just to make sure our gain is 1, let's just use superposition. So let's set Vref to be 0. So Vref is 0, then this is effectively grounded. And what's the voltage of the positive terminal? The voltage of the positive terminal is going to be Vn times 3.3K divided by 3.3K plus 10K. So just voltage divider there. So 33 point. So it's going to be 0.77 times Vn about is going to be the voltage of the positive terminal, which is going to be the voltage of the negative terminal. So what's Vout going to be? Vout's going to be that voltage times RF over RG. Or sorry, it's going to be, so with this thing set to 0, this voltage here, this is a standard non-inverting amplifier. So it's going to be the voltage of the positive terminal times 1 plus that ratio of resistors. So 1 plus 10K over 3.3K, sorry, 1 plus 10K over 33.3K is 1.3. 1.3 times 0.77 is 1. Yeah, so we do get a gain of 1. So we get, so calculating this, V out in this case was equal to the VP, which was VN times 33.3 divided by 33.3 plus 10 times 1 plus 10K over 33.3K equals VN. So yeah, so just by, we were able to test that the input, the gain the input sees by superposition was just 1. Now let's check that offset. So as our next sanity check. So let's do it the other way. Let's set Vn to 0. So Vn is 0. And I got some metal filings on this. I got metal shavings here on my, I'm in a shed and I do some metal work in here. So there's stuff all over this. Now let's check that offset. So now the offset, so now this is 5 volts, our reference. So now let's set the input to 0. So if the input 0, we should see 1.5 volts at that output. Let's see if that's true. So if the input is set to 0 and then my offset voltage is 5, this voltage to the positive terminal, this voltage to the positive terminal is going to be 5 volts times 10K divided by 10K plus 33.3K. And then the overall output voltage is going to be that times 1 plus 10K over 33.3K. And that is 5 times 10 divided by 43.3 times 1 plus 10 divided by 33.3. 1.5. So just as a quick sanity check of that design example, we were able to get, yeah, in fact, this looks like we have a gain of 1 and an offset of 1.5 volts. And we could have derived the equation from scratch. It probably would have taken the same amount of time. But sometimes if these get a little more complex, that's not necessarily an option we're going to have. So this is us using this reference document to produce a desired gain and offset. Let's just look at some of the other examples they have there. So let's look at now a couple things to note about this. This configuration here is a little bit strange because unless Vn and Vref are equal to each other, one of them is going to have positive current, one of them is going to have negative current. So unless these are equal to each other, one of these is going to have a current flowing into it. And normally input voltages can't do that. Normally you can't have current flowing into your input voltage. The exception is, if your input voltage was generated by an op-amp output, an op-amp will sink or source current as necessary to maintain its desired output voltage. So Vn probably in this case should be buffered. If it's a weak signal or if it's anything other than a perfect ideal source, it should probably be buffered by an op-amp. Vref, there's this question of, and students present this a lot of, well, if our circuit's powered by 5 volts, and if Vn is higher than 5 volts, well, it can't be in this case, but if it were, just as the general case, then we have current flowing into the 5-volt supply. And a lot of students get worried about that because they say, well, my circuit's powered by 5 volts and I have current flowing into my 5-volt supply. Is that going to cause its voltage to increase? The only time that's going to cause its voltage to increase is if you have a current that comes from a separate isolated supply. So if your whole circuit is powered by 5 volts, your circuit's probably not going to just be magically generating energy. You know, it's your circuit, parts of your circuit are going to be drawing current. And even if some parts of your current are feeding current back into the 5-volt rail, well, your circuit's probably going to be consuming more current than it's giving back. There are exceptions, of course, you know, but normally it's okay. So the only thing that really a concern with a supply maintaining 5 volts is if it's ever taking in more current than it's putting out, you might get a case where the supply voltage tends to increase. There are design cases where that happens. If you have a circuit powered by 2 isolated supplies, it is possible, or even 2 non-isolated supplies, it is possible to have one supply cause current to flow into another supply, which causes its voltage to exceed the actual desired supply. So most supplies have what's called single quadrant operation, which means they provide a positive voltage and they can only provide a positive current. So just something to be wary of when we're doing designs like this. Op amps, though, the output of an op amp is great. The signal at the output of an op amp can have current flowing in, current flowing out, you know, whatever it needs to be, it's going to do what it needs to maintain that voltage. So, all right, let's look at the circuit for positive M and negative B. And before we scroll down to the circuit, think about it. Okay, if you want a positive gain is typically going to have the input connected to the positive terminal of the op amp. And you want to have a negative offset. What are some ways you could do that? Well, a negative offset could be provided by just any voltage at the negative, you know, any input at the negative terminal. So we could do this with a difference amplifier, right? We could have a difference amplifier. If we have the negative side of the difference amplifier be our reference signal, we could have, it's basically subtracting that offset. And we could have the positive side be our signal. So I would think this circuit could be a difference amplifier topology. Let's see, am I right? No. No. Well, sort of. It sort of is, right? I mean, yeah. Okay. Yeah, so they're just taking the input. The good thing about this is the input is going directly into the positive terminal, which means this is an ideal input. This is a high impedance input, which the difference amplifier circuit is not. A difference amplifier circuit is not a high impedance input. It's because it goes through that voltage divider. But then they basically they take out your reference voltage, divide it, and then use that as the negative input to this amplifier. This is not ideal. You have 2 cascaded dividers here, so there's going to be loading effects here. And I should have looked at this document more, but there's going to be loading effects here, so you can't always do that. And it looks like, oh yeah, they recognize that there's loading effects. So they show it with a buffer, which I don't I don't like this way of doing. Just buy an extra op amp from Texas Instruments to make this work. Probably in this case, I would use a difference. So a difference amplifier is basically the same circuit, but instead of the division happening here, the division happens over here. So you would have a reference signal, provide whatever gain is necessary to have that reference signal properly gained and to the right value, and then you would attenuate the input as needed so that when it experienced that gain, anyway. This is fine, but this is probably not the way I do. I'd probably go with a difference amplifier topology for this if you can. Depending on your reference, you might not be able to do it. You might have to buffer a reference to get that off, to get that new reference, VREF star. You might always have to do that, but this is typically a case where people would use a difference amplifier. Although the benefit here though of doing this design is that input is clean, whereas difference amplifier is not. But if you're buffering, if you're buffering. Okay, let's look at their negative M, positive B. Oh, let's not look at it. I didn't see it. Negative M, positive B. So negative gain, positive offset. Well, again, you could use a difference amplifier. You could have your input signal on the negative side of the difference amplifier, and you could have your offset on the positive side of the difference amplifier. So look at that. That's what they did. so all right. So they did use a different amplifier here, where their offset is generated by the positive side, and their input is on the negative side. So, and again, negative M, positive B. If this V in went through an inversion stage beforehand, then this becomes a positive M, positive B. So you can use this to calculate positive M, positive B also. If you want to just buffer your input here, just have your input go through an inverting buffer, that would work. So, or if your output goes through an inverting buffer, it's going to invert the reference too. But negative M, negative B. So this is they just use a summing amplifier. So if you want negative gain and negative offset, they just use a summing amplifier. And the cool thing about negative gain, negative offset is if you invert this output, then you absolutely, that's positive M, positive B. So a summing amplifier is a really great tool for providing gain for a signal that's adjustable and providing offset if you want. And you can combine multiple inputs, right? You can sum multiple inputs. The downside of the inverting amplifier is it negates, and it negates, and so it's a shunt, right? So it negates, and it's a non-ideal input because you have your input goes through that resistor. So in this case, Vin sees the resistance RG1, Vref sees RG2. But yeah, summing amplifier is an easy way to provide negative gain, negative offset. And again, you can invert it afterwards if you want. So it looks like this document also goes through a couple ways to filter. So filtering is very common. We don't really do it in this class. This class is mostly only dealing with DC, DC systems. We will talk some about some other effects, but filtering is good. If you're doing an actual application, a lot of times filtering is pretty important for stability for the op amp. It's an easy way to eliminate frequency. If you're trying to do an audio, say you have an audio signal and you're trying to amplify an audio signal, you might as well filter out frequencies above 20 kilohertz. Why? Because signals above 20 kilohertz are never going to be the audio you care about because humans can't hear that. So you might as well filter it. And in other systems some systems can have very high frequency noise that can sometimes be very big. Filtering is a nice way to avoid instability because at high frequencies, it's possible for a signal at a very high frequency to become sort of phase inverted through the op amp to make the op amp go unstable. You'll talk about that gain and phase margin in the follow-up to this class, but this is a guide. This guide sort of helps you through that stuff as well. So this would be a good thing to come back even after you take the follow-up to this class as a nice little reference. And I use these a lot. And one of the big takeaways, the reason I want to do this video is when you work for a company, when you leave school and go work for a company making the big bucks, you're very likely not going to necessarily have your textbook. I don't know. The Franco textbook, if you're Todd Morton, you're going to have that thing on your shelf probably for 40 years. If some students probably want to throw that in the circular file as fast as possible. I think once you get familiar with the Franco method, it becomes a pretty valuable resource. But if you don't have it with you, these application guides are sometimes a really valuable resource too. So a lot of times these are a free source for information. The only thing, as I mentioned, the only thing that you really want to keep in mind is you want to know that this is produced by Texas Instruments trying to sell you Texas Instruments. So in this case, it's fairly benign. These are fairly standard things. In more specific applications, they'll kind of be trying to shift you towards Texas Instruments products, which maybe that's fair, right? Maybe if you're a designer, you don't want to spend a week trying to figure something out, trying to reinvent the wheel. You might just say, look, TI has this application done. They have this design guide for me. It's worth it if we pay an extra 10 cents for this amplifier to avoid having to pay me the big bucks for an extra week, right? That's sometimes a fair trade-off. So I wanted to show this. I wanted to show you this. This is posted on Canvas. It's a helpful design tool. And that's it. That's all I've got. So the video after this, we're going to use this design that we just did. So we just did this design to provide a gain of 1, offset of 1.5. I'm going to use that circuit without explaining how I got it in the follow-up video to this. So just be aware that when I just start throwing up this 10K and 33.3K resistor op amp network, that this video is where I got that from. So thanks for watching.